In this video I am going to explain the Adder-Cum Subtractor, particularly 4-bit Adder-Cum Subtractor with a parallel adder. Let's start. So your adder already in my last video I have explained how to design this parallel adder in MULTISIM as well as in VHDL coding. Now as we know, the subtraction is nothing but your addition only, but addition of 16-bit, addition of a negative number. Okay, so if the minor or the subtrahend can be represented in a 2's complement form, then we can have the subtraction through addition only. That means, suppose for example, I will take this as an example. So in this example, suppose in this example I would like to add subtract this better I will make it in a separate one. Okay, so in this suppose this is my two numbers, 4-bit adder and subtractor. That is subtraction of this 4-bit number. Okay, so for the subtraction, B0 is being subtracted from A0, B1 is subtracted from A1, like that. Okay, suppose it is a lower number being subtracted from the higher number. There is a restriction that we are subtracting a lower number from a higher number. Okay, now in this case, if this B, number B, which is subtracted from A, if we represent this negative B, because subtraction is nothing but an addition of negative number, A minus B is nothing but A plus minus B. Okay, so in that case, if we represent this negative B in some number systems like in 2's complement representation, then it becomes an addition. Now how will you do that? Okay, how will you do that in a particular adder systems or in a 4-bit adder system? So if suppose this B, if we represent it in a 2's complement form, now we know that the 2's complement is nothing but the 1's complement plus 1. Now that can be done using a NOT gate and then plus added with 1 to make it 2's complement. The thing is that NOT gate will always do the complementing, but here we are going to design a single circuit in which we can perform addition as well as subtraction also. So as you know, the XOR gate, the truth table, say for example in a 2-input XOR gate, the truth table is when both the input is 0, output 0, when both the input is 1, output is 0, and when both the inputs are not equal, so 0 1 and 1 0, then output is 1. So from that we can conclude that the XOR gate, if any one of the input is 0, then the output is following the other input. Okay, so that means in an XOR gate A, B, suppose the inputs are A and B, then A is suppose always 0, so then the output will be B. But in an XOR gate where the inputs are A and B, if A is suppose 1, always 1, then B output will be the B complement. Okay, B complement, because if you look at the truth table of XOR gate truth table, suppose it is A and B and output say Y. Okay, 0 0 output 0, then your 0 1 output 1, then your 1 0 output 1, and when it is 1 1 output 0. That is the XOR gate truth table. Okay, so as you can see, any input is 0. This is one input 0. This is another input, in another case 1 input 0, this is in another case 1 input 0. So when it is 0, output is 0 because B is 0. In this case A is 0, output is 1 because B is 1. In this case B is 0, output is 1 because A is 1. Okay, that means any input to the XOR gate is 0, output is just the other input. Similarly, if any input is 1, output is the complement of the other input. Any input is 1, output is the complement of the other input. Any input is 1, output is the complement of the other input. So that means in that case that the XOR gate can be used as a buffer as well as inverter through a control pin. Okay, suppose there is an XOR gate and I would like to make it a buffer. So what I will do, I will make any one of the input 0, and whatever be the other input, that will be the output. That is just a buffer. And when I like to make it as an inverter, then what we will do, any one of the input I will make it 1 for all forever, and output will be the complement of the other input. Okay, so in that case what we will do, since suppose this is your 4-bit parallel ladder, this is your 4-bit parallel ladder in which this A0, this is your B0, A1, B1, A2, B2, and A3, B3. Now what I will do is this B, the B which is to be subtracted, B is applied through an XOR gate. Okay, so B0 applied here, B1 applied here, B2 applied here, B3 applied here. Then with a control signal say M, this control signal when it is 0, what will happen? When it is 0, one input of the XOR gate is 0. Okay, so when any input of the XOR gate is 0, sorry, this is not the bubble, this should not be the bubble. When any input to the XOR gate is 0, then it will be the output of the XOR gate will be the same as that of the other input. So what is the other input? B0. So here will be B0, here will be B1, here will be B2, and here will be B3. So that means when M is 0, A0 is already there, you will get B0 here, A1 is already there, B will get B1 here, A2 is already there, and you will get B2 here, A3 is already there, you will get B3 here. So that means this particular adder will act as a adder, only the adder. Okay. Now suppose this M is 1. When this M is 1, so any input to the XOR gate is, one of the input of the XOR gate is 1. So when any input to the XOR gate is 1, the output is the complement of the other input. So here you will get B0 bar, here you will get B1 bar, here you will get B2 bar, and here you will get B3 bar. Okay. So the B gets once complemented. Okay, B gets once complemented. Now the same signal applying as a carry in of the first full adder. If the same signal, I mean same 1 is being applied as a carry in of the first full adder, so what it will do? It will add first this 1 with these numbers. So already this B0 bar, B1 bar, B2 bar, B3 bar when M is 1 is available. Along with that, that means that is the first complement, and along with that, that same 1 is applied as an input, carry in input. So that 1 get added, it becomes 2's complement, and then A0, A1, A2, A3 are there, so together it will be added. And finally, as per the method of 2's complement, method of subtraction, it will give you the result of subtraction of B subtracted from A. Okay, but there is a restriction in this case, that this particular circuit will subtract a lower number from the higher number only. Because if it is a higher number, that means suppose 5 minus 7, that is 7 is greater than 5, so that means you are subtracting a higher number from a lower number, then what will have? In this particular case it will do that, but there will be an end around carry. If there is an end around carry, as per the method of 2's complement subtraction, you need to recomplement the output. So in this particular circuit there is no provision for that. recomplementing the output when end around carry is 1. Okay, so therefore in this method of subtraction, you can using this circuit you can subtract only a lower number from a higher number. You can do the higher number from a lower number also, but the result will not be correct. Okay, so let's see how it can be done in the multisim. So in multisim, as we already know that there are full adder blocks available. There are full adder blocks available. So this is your full adder block, and I am placing that full adder block here. So another one. Okay, what we'll do is I'll first rotate this 90° clockwise. Okay, so it is full adder A. So I'm now placing it as this as a full adder 2, then say this is a full adder 3, and one more full adder, 4 bit. As many as bit, that many will be the number of full adder. Okay, so as per the circuit, this carry first is the carry in will come from that M, and then carry out of the first goes as an carry in out of the second goes and the carry in. So I will connect that. This is the carry out, so it will go as the carry in of the second, okay, then the second carry out of the second goes to the carry in of the third, okay, and the third carry out will go as the carry in of the fourth. Okay, then what I will do is okay, so then I'll use for A and B. So then I'll use this source, binary is digital source. Okay, this is digital constant source. What I'll do is I'll rotate it. Okay, this is for A naught, B naught, A1, B1, A2, B2, then A3, okay, and B3. So I'll make it as A, this level I'll make it as A naught, then I'll make it as B naught. Okay, simply double clicking on it, this wizard will open where you can sense the labels, display, value, pins, everything. Oh sorry, this B naught is already there, so it will be A1, then it will be your A2, then this will be your this is A naught, B naught, A1, B1, then this will be your A2, and this will be your B2, then this is your A3, and this is your B3. Okay, so this is your A connected, similarly this is your A0, this is your A1, this is your A1, and this is your A2, then this is your A3. Okay, now before applying this your B inputs, we'll use one XOR gate. So XOR gate is your 7486 7486. So this XOR gate 7486. What I'll do is I'll rotate it. Okay, this is one XOR gate. Okay, so the same I'm copying. Okay, okay, so one of the input to the XOR gate comes from the B input. Okay, and output of this XOR gate will be the B input of your full adder. Okay, now I'll use another signal as M. Okay, this is a okay. Then I'll use another symbol. Source for your M input. So this is your M. I'll rotate it. Okay, so now this M input will go to this, the same will be here. Okay, the same M input will go to the other input of all the XOR gate. So let it be my M. Okay. Now I'll use some indicator. Okay. So this probe, say green probe I am using. I'm rotating it. And this is your sum knot. Okay, and value here instead of 2.5 I will make it 3.5 volt. Okay, so this is your S knot. Same I am copying and pasting here. This is your sum 1. Similarly I am pasting here. This is your sum 2 and sum 3 and one more for carry out. Okay, so this is suppose C out. Okay, so that's all done. Now first of all I'll take this example. This example for addition. Okay, A is all 1, B is 0 0 1 1. Okay, so what I'll do is all the A I'll make 1 1. This is A1, A1, A21, A31. Then B is your B3, B2 0 0. B B3, B2 0 0, B1 1, B2 1 1. Now since it is addition, so therefore this M will be 0. So I am making M 0. Okay, and screen has to be connected from the same M carrying of the first, as it is this carrying is the first carrying is with the M only. So this same carrying is also connected to the M. Okay, now let us save it. Let us save it. Yes. Okay, so I'll save it in my app drive, DBCT, and then Spring 2020 MULTISIM. So it will be Adder-Cum Subtractor. Okay, now let's run it. Okay, as you see, the result is 1. The sum output is S30, S1, S20, S10, S01, and carry out is 1. So S30, S20, S11, S00, as per this, S11, S01. This is, sorry, this one. Something is wrong here. It is 110 here. The result is, this is addition, no? So addition is 110 here, then 0 1 1 1 1 here, and then 1 1 0 here, 1 1 0 here. So 1 0 0 1 0. So 1 0 0 1 0. So that means it is correct. Okay. Now I'll make subtraction. Suppose the same number I am considering, 1 1 1 1, then say 0 0 1 1. Okay. Okay. So if it is subtraction, 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 0 is 1, there is no end around carry. Okay. So carry is 0. So how it is done actually in 2's complement method? This A will be remain same, A will be remain same, and in your B it will be 2's complement. So 2's complement of this 0 0 1 1 is 1 1 0 1, 1 1 0 1. Okay. So then added it 1 1 0 1 1 0 1 1 1 1, then 1 1 0 1. So 1 1 0, then 1 1 0, carry 1 1 1 1 1, then carry 1 1 1 1 1, and there is end around carry, discard that carry. Okay. When end around carry is 1, then discard it, and when your end around carry is 0, you need to recomplement the output. Okay. That means when you are adding subtracting a higher number from a lower number, then you need to your end around carry will be 0. After this addition, here you will get the end around carry 0, and when it is end around carry is 0, you need to recomplement the result. So as I mentioned, in this circuit we can do only the subtraction for lower number from a higher number. Okay. So this will be your result after subtraction. Getting? So the original number is 1 1 1 1, that is your 15, 0 0 0 1, it is your 3. So 15 minus 3 is 12. Now let's see. So the bit position will be remain same, but this will be your 1. Once I make it 1, you see 1 1 1 0 0. As you see, the result is 1 1 0 0, and as I mentioned here, you will get a end around carry 1, because here it will be 0, sorry, here it will be your 1 1 0, then 0, then 1, then 1, and there will be end around carry 1. Okay, but while doing subtraction using two's complement method, if end around carry is 1, you need to discard that. Okay, or recomplementing or the complementing the carry when you are subtracting a higher number from a lower number. Okay, so this result is correct. So this is your full adder, I mean the Adder-Cum Subtractor. So this is a 4-bit full adder. The same 4-bit full adder can be used as a subtractor also by using an extra series of XOR gate with a control pin, which will determine whether this circuit behaves as an adder or subtractor. If it is 0, then it will be adder. If it is 1, then it will be subtraction A minus B, provided B is less than A. Okay. So now I will do it in your VHDL. So this is your VHDL Xilinx platform. Okay. So here we will do the Adder-Cum Subtractor using VHDL code. Okay, so let's go to the new project, file new project. Okay, as we already did in several one in my previous video. So here I'll have to give the name, which is the name of the project, and also with that name there will be a folder created in the designated location. Okay, so let us put it as Adder_Cum Subtractor. Okay. So next, so as I mentioned in my previous video also, this wizard is for setting up the hardware to be connected with the your VHDL, but we are not going to connect any hardware right now, only the simulation, so we need not to do anything with this. So the next, and this gives you the summary of the project, then finished. Okay, after that, so it is showing this. So after this, you need to right click on it, click on the new source, then click on this VHDL module and give a file name. So this file name will be the name of the file, source file, that is with extension .vhd, and along with the same name, this file name will be the name of your entity. So I am putting it as a Adder Subtractor. Adder Subtractor. Okay, so it has to go to this same folder, Adder-Cum Subtractor. Yes, VHDL module is clicked, then add to the project should be saved, then next. So here I will give the input output ports. This is the entity wizard where you will indicate or put your ports, inputs and outputs. For my Adder-Cum Subtractor, the inputs are A0, A1, A2, A3. Which is input. Here I will click it as a bus. So when it is a bus, it will be A3 to A0. Similarly, B is also my input, which is also a bus. It will be 3 to 0. So it behaves as a vector, 3 down to 0. Then what else is required? M as a signal, which is also in, but it is a single signal. Okay. Then what else? Output. So my output is your S is also a bus, which is output, and the bus 3 down to 0, and there is end around carry, so C underscore out. Okay, which is also an single bit output. Okay, so next, finish. So this is the design summary. Okay, then this is the code. As I have mentioned earlier also, this green part is your comment, and the first part of your program is the library. Okay, library declaration. Here also this IEEE STD logic library is okay with this, I mean sufficient for this, and .all means it will take all the files of the IEEE library, which is IEEE.std logic 1164. Then second portion of the program is the entity declaration. As I mentioned, the name of the entity is the same as the name of the file. You see, Adder-Cum Subtractor, the same is the name. So these are the ports that you have declared. A as a vector, that is a bus, A3, A2, A1, A0. So it is showing here STD logic vector 3 down to 0. Similarly, B, M is one signal. Sum means I am defining this one. Okay, A3, A2, A1, A0, B3, B2, B1, B0, M, N, S3, S2, S1, S0, and C out. Okay, then in subtractor, in the entity part, then the architecture behavior is the name of the architecture. The architecture begins here. Now before going to this, what you need to do is, you need to, because it is a structural program, you need to declare the component. So right click on it, add new source. So here there are two components required, one for the full header, another for the XOR gate. Okay, so here I am typing say full header. Okay, FA. So full header, and this is also VHDL module. Next, so in the full header my input A, B and C, and say sum and carry as my output. Okay, sum and carry are my output. So next, finish. So let us now finish up this full header part. Okay, full header part. So architecture begins here, within which I am defining one process. So process is of A, B and C. Okay, so process begins here. Process begin here. Then what you need to do is sum, simply a behavioral modeling of this full header. Sum is assigned with A XOR B XOR C. Then your carry is assigned with your A and B or B and C or A and C. Okay, so here process ended here, end process. Okay, then the architecture behavioral, the name of the architecture is behavioral, and here ended here. Okay, so this way I finish the your XOR my full header component or full header subprograms. Okay, the next is your XOR gate. So for that XOR gate, again XOR say gate. So for that again VHDL module. Next, so for XOR A, 2 input XOR gate, so A, B, then say Y. Y is your output. Okay, then this is the program for your XOR gate. So process here, process A, B, the process begins here. then your y is assigned with A XOR B, and process ended here. Okay, so XOR gate part is also done. Okay, so next go to the main program. So in this main program, before architecture begins, what you need to do is, as it is a structural program, so the structural component has to be declared here. So for that, first I am going to this. So what we will do is, component it has to be defined or declared as it is as it was defined in the subprogram. So here for defining or declaring the component, the keyword is component. I am copy and paste, so n component. Similarly, component the XOR gate. So from this I am copy and paste it there. Okay, n component. So component declaration for both the structural component is done here. Okay, then as you see here in this circuit, A0, A1, A2, A3 are direct input to the full adder. Then for the carry in also direct input M as a carry in, but this C0 as the C in here, C1 as the C in here, C2 as the C in here. Okay, and the output here is the input B here, B0 here, output here the input B1 here, output here the input B2 here, output here the input B3 here. So what I will do is I will define it as a signal. So here I will define it as C0, C1, C2, and say X0, X1, X2, X3 as symbol. Okay, signal. So signal. So C0, C1, C2, then your X0, X1, X2, X3. These are symbol steady logic. Okay, these are the symbols defined. So next is you need to port map all of the components. So for the XOR gate, I'll put it as say U1, U2, U3, U4. Okay. So first let us map the XOR gate. So U1. So what is U1? U1 is the input is one input is your M, another input is your B0, output is your X0. Okay. So what is U1? U1 is your XOR gate. It should be the same as this. U1 XOR gate, then port map. There is a space, port map. So within bracket port map, one signal is this M directly. So here M, another one is your B1 direct input. So B0. Then output is your X0. Okay. And just copy and paste it here. So this will be your U2. UT is also XOR gate. One input is M, another input is your B1, and output is your X1. Same way, U3, one input is M, another input is your B2, output is your X2. Then U4, one input is M, another input is your B3, and output is X3. Then comes the full adder. Suppose this is your full adder A, full adder B, full adder C, full adder D. So let us point it as full adder, say A, which is your this full adder. Where is the full adder component? Yes, it is directly full adder, FA. So FA, then port map. Now in the full adder, first full adder, what are the inputs? Your A0 is directly input. Here it is X0 and M. A0, X0, M. And what are the output? S0 and C0. Okay. So first input is your A0. Then second input is the output of the XOR gate, which is X0. Then third input is the C in, that is your M. Then output is your S0. Here it is directly this S0. So since it was defined as a vector, that is why it is within bracket. S0. Then carry out C0. Okay, carry out C0. That's all for the full adder, first full adder. I'll just simply copy and paste it here. So it is suppose full adder B. So full adder port map. Now here it will be A1, then it will be X1, then here it will be C0, here it will be S1, and here it will be C1. Okay. Similarly, say full adder C, full adder port map, it will be your A2, then it will be your X2, it is your C1, then it is your S2, and it is your C2. Then say full adder D, then the last full adder. So it is your A3, it is your X3, then this is your C2, this is your S3, and this carry out, here we have defined it as C out, this one, final carry out. So it is C out here. Okay. So that's all. Now save it. Something is wrong in the 58, 58, 58. Syntax error. Yeah. Oh, so here you have to put the semicolon. Then in line 50, this colon is not required. Okay. Yes. So that's all. Now you see this Adder-Cum Subtractor. These are the different components. Now we'll check the syntax again. So check syntax for the Adder subtractor. So the syntax is checking. So check syntax completed successfully. That means there is no syntax error. Similarly, I will check this syntax for XOR gate program. Similarly, there is also it is done successfully. Then I will check syntax the full adder program. Okay, so check syntax done successfully. So next is to simulate. So before simulate, what I will do, I will add one test bench. So in the use source, then say Adder Subtractor tbw. So this is the name of the file. So here I will use VHDL test bench. Next, so you see it should be added with Adder Subtractor. Next, finish. So this is your test bench waveform programs. Okay. Yes, these are the ports: ABMS output, ABM input, Cout output. Okay, so here again I will not use this clock. Okay, so this part is also not required, as not using the clock. Okay, so steam process 1. So here we have to make it for A0, A1, A2, A3, B0, B1, B2, B3 as well as N. Okay, so what I will do is all are initialized with 0 initially. So first I will make it as so 0 for say 50 nanosecond. Wait for 50 nanosecond means it will remain 0 for 50 nanosecond. Then A0 will be your not A0. Okay, A0 will be not A0, so clock is not required. Okay, so wait for again 50 nanoseconds. Okay, end process. So this is for A0. So that means for the first 50 nanosecond it will wait as it is 0 initially. Okay, then it will be 1 and it will go for 50 nanosecond wait. Then in the next 50 nanosecond again it will wait as 1, then it will be again 0, and that means for 100 nanosecond it will be 1. First it will first it will be 50 nanosecond, then after it will be 100 nanosecond, 100 nanosecond, 10, 10. Okay, then steam process 2. So the steam process 2, so for 100 nanosecond, it will be 0 only, then it will be 1, then so after that 150 nanosecond, 150 nanosecond it will go on. Then in the steam process 3, in the steam process 3, say it will be 150 nanosecond, then it is your A2, so A2, so first half 150 nanosecond it will be remain 0, then it will make it 1, wait for 50 nanosecond, again wait for 150, so that means from 200 nanosecond and 200 nanosecond it will be this. Then steam process 4, this is 200, let it be 200 nanosecond, so it will be A3, so it in 250 nanosecond, first 200 nanosecond it will be 0, then 250, 250, 10, 10 like that. Then your steam process 5, in the steam process 5, since at the beginning for the 50 nanosecond I am making a 0, so let it start from 100 nanosecond, 50 difference, okay, 50 nanosecond difference. So 100, so let us take it as 150 nanosecond. So 150 nanosecond, then I let it make it 100. So it will be now B. So B. This timing I am giving arbitrarily. So B naught, not B naught, and again wait for 50. So 150, 150 nanosecond, it will be 1010. Then steam process 6, it will be your B1. Now I am making it 150. It will be B1. It will be B1. Then steam process 7. It will be yours 150, no 200, then it will be your B2, this is your B2, then steam process 8, it will be your B3, and this becomes your 250, this is your B3. Okay, then last it is your 9 for M. Now say first 500 nanosecond, so 300 first 300 nanosecond it is 0, then it becomes 1, not 300 it will make, because what I am giving 50, 150, 300, 500, okay, so let it be 500, okay, 500 nanosecond it is 0 only. Then wait for m, not n. That means after 500 nanosecond it will go to 0, as initially this m is also 0. So therefore it will go to n, then wait for say 50 nanosecond, then 550 nanosecond. Okay, so that's all. Now let us check the syntax for this. Okay, check syntax for this is going on. It is successfully done, no error. Okay, then I will simulate it. Simulate behavioral modeling. Okay, it will open up in a new window. So this is your test bench waveform window. Okay, now let's see. Okay. Okay, first of all let us see the m. You see this is your m. M is 0 up till this. M is 0 up till this. Okay, m is 0 up till this. After that m is 1. Okay, now when m is 0, the circuit is adder. So let's see what is A. So take up at any point. Okay, at this point it is A is 0 1 1 0, and what is B? 0 0 1 1. So what will be the output? 0 plus 1. It is adder because m is 0. So 0 plus 1, which is 1 here, then 1 plus 1 0 with carry 1, that carry 1 plus 1 0 plus 0 0 with carry 1. Okay, 1 plus 0 1 with end around carry 0. So the result is 1 0 0 1 with carry out. So where is the carry out? This is the carry out, which is 0. Similarly, take up another part. Suppose let at that point. So here the A is 1 1 0 1, B is 1 1 0. So and m is also 0. Since m is 0, so it will be adder only. This 1 plus 0 1, this is 1. Then 0 plus 1 is 1. Then 1 plus 1 is 0 with carry 1. 1 plus 1 with carry 1 1. So 1 with carry 1. It's correct. Let us check in another point, say at this point. Okay, at this point where m is 1. When m is 1, it has to be subtraction. Okay, subtraction. So 0 1 0 1 is A at that point, then B is 0 1 0. So then okay, so 1 minus 0 1, 0 minus 1 is 1 with borrow 1, so it becomes 0. So 0 minus 0 0, or simply it is 5, this is 2, result is 3, and here you will get end around carry 1 because it is doing using 2's complement method. Okay, let us take another one. In this case you will see this is 10019 and 1101, it is here 13. Since it is 13, it is greater than this, so therefore end around carry is 0, so result is also not correct. Okay, so that way, as I mentioned, this is for subtracting a lower number from the higher number. Addition, there is no problem. Okay, so this validates the truth table or the logic. Next we will see your circuit or the schematic, RTL schematic. So double click on it, RTL schematic. This RTL schematic is running. Since it is a larger circuit, it takes some more time. Okay, so it will open up in a new window. Yes, this is the Adder subtractor. This is A bus, B bus, S bus, C out, and M is a single signal. XOR gate block here, full adder block here. So this is your full adder block. This is your XOR gate block. There are a few options. You can see the detail here. What are the signals, input, output, all this, and different pins you can see here. Then instances. Okay, so let us now see the technological schematic. So this is the complete technological schematic of the complete block. You can see the inner part. This is your A XOR B part. This is also your adder block, like that, adder block. This is also adder block. So likewise, this is A, B, A, M, B, sum, carry out. Okay, so that's all. So in this video, what we have seen, we have analyzed the Adder-Cum Subtractor using a 4-bit parallel adder along with an XOR gate, and that same is implemented in your MULTISIM. Okay, and in the VHDL, and in the VHDL structural code, structural modeling using full adder and XOR gate as a component. Hope you understood. Thank you for listening.